The third example shows the solution of using general power rule in a rational function which requires quotient rule. Welcome to differential calculus. What is the general power formula? Comparing the two power formulas, the first is simply called power formula. The derivative of x raised to n is the exponent n multiplied by the variable x, this time raised by the original exponent less 1, with the derivative of that variable x all over dx. With this formula, the derivative is its at simplest form. In this case, it's x, which, when used with chain rule, provides dx upon dx, which instantly cancel out. The general power formula, on the other hand, has the same format, although instead of just a single variable x, a function is involved, although it is simplified in the formula as u. The procedure is the same, which has the exponent made into a coefficient times the function raised to n minus 1, with the derivative of u with respect to x. With such format, we can no longer cancel out du with dx, as du is still a function. The rational function for this video is y is equal to the square of the quantity 3x minus 1 over x squared plus 3. Even if the denominator is very evident, because of the exponent 2, work on general power rule before the quotient rule. So move the exponent as a coefficient, making dy over dx as 2, with the ratio raised to 2 minus 1. Then multiply to this the derivative of the rational function, d all over dx of the quantity 3x minus 1 all over x squared plus 3. Focusing on the derivative part, employ the quotient rule. So copy all other components of the derivative. Those are 2, and the rational function with the square of the denominator, which is the quantity of x squared plus 3. The numerator follows the lower term multiplied by the derivative of the upper term, less the upper term times the derivative of the lower term. Now that these are only found in certain areas of the numerator, so the next thing to do is to distribute d over dx to all involved terms. dy over dx is twice of the rational function times the denominator, which is square of the quantity x squared plus 3, where the numerator becomes the copied x squared plus 3 with the distributed derivative of 3x and derivative of 1. Subtract to this the copied upper term with the distributed derivative of x squared with d over dx of 3. The derivative of constants are 0, thereby reducing the long function. The next step is to move constants outside the derivatives. So dy over dx is taken as the copied terms of twice of the ratio of 3x minus 1 over x squared plus 3 with the expanded quotient rule, which contains x squared plus 3 with the constant 3 and the derivative of x. Then also the quantity of 3x minus 1 with the derivative of x squared, as there are no coefficients in the term. Simplify the function by cancelling dx upon dx, so the derivative then becomes the copied terms with the ratio having the numerator of the quantity of x squared plus 3 multiplied by 3, minus the other quantity of 3x minus 1 times the derivative of x squared, which is 2x times dx upon dx. Another dx over dx is observed, and we cancel it again as 1. And this marks the end of differential calculus. The next thing to do is to simplify the terms through algebra, so reduce groupings and multiply terms. The first is x squared with 3 as 3x squared. Then 3 by 3 as 9. The other pair has negative 3x times 2x, making negative 6x squared. Then the negative of negative 1 times 2x is positive 2x. The next thing is to collect similar terms in the numerator. So the derivative would have the third term as negative 3x squared plus 2x plus 9 upon the square of the binomial x squared plus 3. At this point, there is nothing much to do from the numerator, but we can combine denominators. Thus, the final derivative becomes twice of the binomial 3x minus 1 times the quantity of negative 3x squared plus 2x plus 9, all upon the cube of the binomial x squared plus 3. Even if we expand quantities further, there isn't any reduction from the numerator and denominator, so we keep this as the final answer.